and welcome to UIC's Engineering Expo for 2021. We are Team 35, and this is our Inchworm robot. Team 35 consists of Ulmer Durrani, Matt Halverson, Daniel Kulak, Alex Lewandowski, and Michaela Saravat, all of whom are seniors at the University of Illinois at Chicago's College of Engineering. Nature has evolved numerous methods of movement, allowing for animals to better use their bodies to navigate the world around them. In light of this, some animals are better equipped to navigate different environments and terrains. Studying the locomotion of different creatures has made the creation of robots that mimic their movements possible. The goal of this project was to create an inchworm caterpillar robot capable of utilizing the two-anchor crawl gait of an inchworm caterpillar in both forward movement as well as turning. The underlying motive for the project was to develop a mechanism that would allow a robot to move in this fashion and discover what might be learned from attempting to mimic nature in this way. The video on the left shows an inchworm caterpillar in nature, and the video on the right shows a robot designed to mimic this type of locomotion. For this project, our goal was to design a robot capable of not only moving forward in this fashion, but also to turn this way. An inchworm gets around using something called the two-anchored crawl gait. The inchworm will begin in a loop with its front and back legs very close together, causing its middle section to loop above its feet. Next, it will lift its front legs up, using its rear legs as an anchoring point about which to pivot. Then it will put its front legs down in such a way that its body is fully extended in the direction it is traveling. To complete the cycle of motion, the inchworm will pull its rear legs forward to the location of its front legs, once again forming a loop. The primary goal of this project was to create a novel mechanism for this locomotion, as well as generate a motion that produced a more pronounced loop than previous inchworm robot designs have in order to better represent the original locomotion. Other considerations such as speed, scale, and practical applications were not particularly important since the motivation for the project was solely research-based.
In order to achieve the two-anchor crawl gait, anchors needed to be devised. In order to help the group better conceptualize this, we divided it into two main sub-assemblies. We have a front foot and a rear foot. So this slide focuses entirely on the designs we came up with for these feet. These are the biggest ones that we had considered, though there were a few smaller ones. This first one here is a one-way wheel design, and the reason it's got that name is this red component in the assembly pictured here is actually a one-way bearing that allows the wheel to roll forward but not in the reverse direction. So this would allow us to effectively lock the wheel from sliding backwards while the body actuates, and then once the robot contracts, it pulls the rear end forward. The second concept that we had considered early on was an electromagnet design, but this was quickly ruled out due to two main reasons. First is the power requirement for powering these magnets, and the second problem is that this would restrict us exclusively to magnetic surfaces, and we wanted to try and make our robot as versatile as possible. Now the third design we looked at was a gecko tape design. The gecko tape is a really interesting product that we found while researching different ideas for the feet, and it's a material that is sold in sheets that leverages van der Waals forces to stick to surfaces without adhesive. Some massive advantages of this is it's incredibly lightweight, and because it comes in these sheets, we could fit it to any footprint that we so choose. However, some disadvantages to it is that it needs to be lifted up straight vertically, or as close to straight vertically as it can be in order to disengage. Another disadvantage is that after the pad collects enough debris, it loses that adhesion quality about it.
In addition to front and rear feet, an arching body section is required to achieve the two-anchor crawl gait of an inch. To create this arched body, the team considered several methods. The first was traditional linkages, which were rigid and easy to control. However, it was difficult to achieve turning without an excessive number of actuators and joints. Additionally, the team considered embedding shape memory alloy into a soft material, which allows for organic and complex shapes which can be recalled with an electronic current. The team then considered a slinky-like structure, which could have tendons running through it, the tendons being pulled by actuators, bending the slinky shell into desired shape. This, unfortunately, was also very difficult to control, as the shell is a circle, which increased our degrees of freedom drastically. To counteract this, and the final design we picked was a stack of discs, which are also actuated by tendons with flat mating faces that are held together by a central elastic spine. This allows for a curve in any of the 8 directions, which are the flat faces in the discs, and holds itself together and springs back into its neutral shape when tension is released.
The electronics consist of 2 Adafruit stepper motors connected to 2 SparkFun motor drivers. Everything was controlled by an Arduino Uno using the Excel stepper library, which can control precise speed and positioning of multiple motors simultaneously.
Our final design consists of octagonal discs that provides a distinct mating surfaces. There are 4 tendons attached to the body to control the motion. These tendons are secured at the front and the rear end of the assembly so they can be contracted. The inner tendon acts as a spring for the stack, bringing it back to the alignment. The picture on the right shows the hole pattern for the tendons. The middle hole is for elastic tendon, while the outer holes are for actuation. Let's take a look at the video.
The tendon actuation method of the robot went through 2 major iterations. The first involved attaching all 4 tendons to a plate, which is rotated by a 2-degree of freedom gimbal, which can be seen on the right. Although the gimbal automatically accounted for the different changes in length necessary for each tendon by tying them together, the stepper motors used were unable to overcome the added resistance and mechanical disadvantage of the mechanism. Our final actuation design can be seen on the left, and simplified the gimbal into 2 pulleys, each with 2 tendons attached. By actuating the pulleys in different directions, tendon contraction very similar to that created by the gimbal can be achieved.
Now, if we talk about the front foot and the rear foot of the robot, the front foot segment is responsible for the anchoring of the body. To solve the anchoring problem, we used gecko tape. Now, in order to move the robot forward, the gecko tape was released. Moreover, the front foot needed to be lightweight to ensure that the motors at the rear end had enough power to lift the front segment. On the other side, rear foot was designed to be the heaviest segment of the robot as it housed the motors, electronics, and the mechanical components that were used to control the body. We also wanted the rear end to be light enough so that when the body segment arches, the anchoring of the gecko tape is strong enough to allow the rear end foot to move forward. This led us to the design consisting of 2 motors, 2 wheels, and a mechanism to control the contraction of the tendons.
Here, we can see the robot achieving its 2-anchor crawl gait. Overall, the stacked disc body concept has been proved. While improvements can definitely be made in actuator selection, perhaps employing linear actuators or independent actuators for each of the 4 tendons to allow for more precise control. Additionally, assembly techniques could be improved, which would again allow for more precise controlling by evening the tension at the equilibrium point between all 4 of the tendons. Switchable clutches on the rear wheels additionally would enable more effective turning, as right now 1 wheel has to drag across the ground anytime a turn step is completed.
We would like to thank our sponsor, Professor Bouncel, for giving us the opportunity and experience to build a robot from scratch and for working through design ideas we had along the way. We would also like to thank our advisor, Professor Alonso, for guiding us and keeping us on track every step of the way. We'd also like to thank everyone at the Makerspace, especially Eric and Dylan, for their time, guidance, and help with some problems we had.